Hello, I'm Clinton Herget, Senior Solutions Engineer at Snyk. Today's session is called Securing Your Container Build Pipeline. In my first session, called Building Secure Containers on the Developer Desktop, we focused on using Snyk's local build tooling to find, fix, and monitor for security vulnerabilities in container images from within the developer's experience. In this demo, we'll be extending that story to cover the next phase of the software development lifecycle, and using Snyk within the merge, build, and deploy phases of your workflow. Finally, in my last session, we'll conclude by showing how Snyk can help to proactively monitor for new container vulnerabilities once your applications are deployed to a production environment. We'll start by revisiting the Secure Container SDLC and review why developers have such an important role to play in container image security, but also why it's critical to secure the pipeline itself. That can begin as early as the source control management or git merge phase, and so we'll show an example of how Snyk Container can be implemented as a PR check by looking directly into your Docker file for potential base image vulnerabilities, and discuss the advantages and disadvantages of this approach. Next, we'll move into the continuous integration or build phase of the pipeline, and discuss strategies for automating container tests, providing the option to fail the build attempt after the container image is created, but before it gets deployed. We'll go over Snyk's native plugins for a variety of common CI pipeline tools and also touch on ways Snyk's command line client can be used within a build process to offer several advanced features. Then we'll show a live demo of how these various strategies can work within a Jenkins pipeline as we build and deploy the sample web application I introduced in the first session. And finally, we'll conclude by discussing the importance of monitoring your container images from CI to protect against future vulnerabilities. In our last talk, we introduced the concept of the Secure Container SDLC, and I talked through the local development phase, in which a developer selects an appropriate base container image, adds additional user layers to support the application, then builds and tests the images locally. But of course, that's just the beginning of the process. Once a developer commits and pushes new code to a branch, the usual workflow is to create a pull request or merge request and integrate their changes with the mainline development branch. At that point, a series of automated processes take over that together make up the DevOps pipeline. Typically, this starts within the source code manager, a tool like GitHub, Bitbucket, or GitLab, which runs a series of PR checks to test the quality of the new code and can be used to enforce certain standards, like linting, which can be determined by looking at the code itself before a build is initiated. Let's take a look. In our last session, I introduced this web application, which is based on the Symfony PHP framework, and created a Docker file to allow it to run inside a container. I'm going to introduce a new PR to that Docker file, but in this case, I'm actually going to revert the security improvement we made last time to show the effect of reintroducing some vulnerabilities into the container image. This is the first place that Snyk Container can provide valuable insights into container vulnerabilities. We've recently released the ability to test Docker files directly as part of the PR check process, the same way Snyk can look at your open source package manifests. A webhook is added to your Git repository, which will initiate a Snyk test when a new PR is created. But it's important to note that because this check happens before the container build, the mechanism is different. Since the build context and tooling is unavailable, we're actually parsing your Docker file directly to detect the base container image being used, and then providing a list of vulnerabilities from that base image without taking user layer modifications into account. So you can see here that Snyk has detected new vulnerabilities in my PR because of the base image regression I just introduced, so this branch can't be automatically merged into my main line. If I want to find out more about why Snyk has failed this check, I can follow the link back into Snyk to get a full vulnerability analysis. So this Docker file is now a first-class citizen within Snyk, and will monitor those base image vulnerabilities proactively and notify you as new ones are detected. As you can probably tell, this sort of check is fundamentally different from the deep image-based testing Snyk offers via the CLI and will later implement within the build pipeline. So there are advantages and limitations to using the Git-based Docker file approach. Because the PR check lives alongside Snyk's other security solutions for open source dependencies and infrastructure as code scanning, it can be easy to test your Docker files at the same time since the webhook is already running on your repositories. But it's best to see this test as an early sanity check against potential regressions being introduced by your base container images, or as a way to detect newly discovered vulnerabilities in those base images you've already been using, since we proactively retest the images every day and will notify you when new vulnerabilities are detected. In the future, we'll also be offering the ability to introduce fix PRs, automatically upgrading your base images when newer versions become available, the same way we currently do for open source packages. But the primary drawback to Git-based container testing is that because it's scanning your Docker file directly, there's no visibility into what actually ends up in your container image as a result of the build. Therefore, results may be different from other integrations that are looking directly at the image file system. Additionally, this means the test lacks a point-in-time reference, so the report only reflects the vulnerabilities in the base image as it would exist if the build took place at the moment of the test, rather than the dependency tree of a specific build. And finally, while there are configuration options to control the PR check failure state, for example, you can tell Snyk to fail the check only in the presence of high-severity vulnerabilities, or only when the PR is introducing net new CVEs that were not already present in the target branch. But as we'll soon see, you can introduce a lot more granularity into these pass-fail decisions by integrating Snyk as a build pipeline step later in the process. So taken all together, Docker file scanning should be seen as a useful addition to your secure DevOps toolchain rather than a replacement for deep image-based scanning during the build phase. So after code is merged into a mainline branch, typically a CI pipeline tool is listening for new commits and kicks off a new build process, which is a series of steps to compile, test, package, and deploy the new release, including building the containers. Snyk Container can integrate as one of those pipeline steps, ideally after the image is built, but before it's pushed to a container registry. There are a number of continuous integration toolchains available, but Snyk has native plugins available for several, including Jenkins, CircleCI, TeamCity, Bitbucket Pipelines, and Azure DevOps. But those aren't the only options. Because each of these plugins is backed by Snyk CLI, as long as you're using a build process that can run a Linux, Mac, or Windows binary, or a custom container image, you can easily add Snyk into your pipeline. There are multiple strategies for setting up a gated process within CI for vulnerability scanning, and the exact implementation will depend on your team's security policies, but Snyk is designed to be highly customizable. In general, you can think about gating in one of three ways. A permissive policy which allows all builds to succeed regardless of the underlying container vulnerabilities, but still use Snyk to generate a build artifact or record of the security issues that are found for later remediation. Obviously, this strategy maximizes velocity at the expense of security, because vulnerabilities are still able to be deployed before the remediation loop is closed. At the opposite end of the spectrum, a blocking policy can ensure that any build in which container vulnerabilities are found will fail. This is likely to be an unpopular policy with developers because it minimizes velocity in exchange for maximum security, ensuring that every vulnerability must either be remediated or have an exception created before that release can be deployed. And finally, there can be any variety of custom policy, which uses logic specific to the organization or to the project to determine on a case-by-case basis whether a container is deployed to a registry. This may take into account things like, what are the severity of the container issues found? Are the issues new? In other words, being introduced within the delta between this build and the last one? What specific weaknesses are the CVEs related to, etc.? This approach attempts to strike a balance between velocity and security, but it does require some upfront setup in terms of policy setting and technical implementation. There are many ways to set custom security policies within Snyk, and I encourage you to check out some of our other sessions on the topic. So with that in mind, let's revisit our demo app and look at how Snyk can easily be used to adopt any of these three gating strategies in the context of your CI pipeline. I'll be using Jenkins as my example here, but the same concept should apply regardless of your toolchain. And for you Jenkins nerds out there, though I am showing a freestyle job here, all of these options are available for pipeline jobs as well, so you can easily add Snyk directly to a Jenkins file. I've already installed the Snyk Jenkins plugin and authenticated with my Snyk token. I've set up a job with some basic steps involved in building and packaging our containerized web application. Again, we're working with PHP here, so there's no need to compile anything, but we do need to install application dependencies using Composer, the PHP package manager. Once that's done, we can run a docker build command to use the Docker file to create our container image. And finally, I'm running a Docker push to send that image into a container registry. In between those build and push steps is where I want to integrate Snyk Container. As we've already discussed, Snyk doesn't specifically require a Docker daemon, so if you're using something like Rocket to build your containers, or if your build process itself is containerized and there's no Docker socket available, no worries. You simply need to provide an OCI-compliant container image for Snyk to scan. But in this case, I've mapped a Docker socket into my Jenkins container to perform the build and push steps, so that's what Snyk will use as well. Out of the box, Snyk provides configurable support for both the permissive and blocking gate strategies. You can easily set whether to fail the build if issues are found, or allow it to succeed. Regardless of the failure state, Snyk will generate an artifact containing the results of the container vulnerability test. You can also easily set the failure state based on the severity of vulnerabilities, and this is something that can be further customized by setting a Snyk security policy for your organization to modify the severity rating based on a combination of project attributes, exploit maturity, vulnerability type, and other criteria. Because the CI pipeline plugins utilize Snyk CLI behind the scenes, any additional client arguments that can be passed to the CLI can be passed through the plugin. So to indicate I want to test my container vulnerabilities here, I'm passing the --docker argument. I'm also specifying the file attribute and indicating I want Snyk to associate my Docker file with the image scan results, which helps provide more detailed remediation advice. There are many other options I could pass in here, including exclude base image vulns. As we discussed last time, this flag can be used to filter out any vulnerabilities that already existed in the base image of your container, so Snyk will only flag issues introduced by your user layers. This is particularly useful in multi-step container builds in which one team manages hardened base and middleware images, which are then customized by app dev teams. Passing this flag ensures your builds won't be blocked by vulnerabilities that aren't your team's responsibility. Let's go ahead and run our build. Of course, this would normally happen automatically when a new commit is pushed to a monitored branch. Our pipeline installs the application dependencies and then builds the container image from the Docker file before running the Snyk plugin. Now, because I've configured a blocking gate based on the presence of any high-severity vulnerabilities without passing the exclude flag, I expect Snyk to fail this build due to the high-severity CVEs that still exist in my base container image. If I want to investigate the specific vulnerabilities behind that build failure, I can look at the build artifact that Snyk generated. This is a packaged HTML report containing the test results associated with this specific build, including all of the information you'd see in the Snyk CLI or user interface. If you watched the last session, you'll remember that our CLI has a JSON output mode, which exports all of the vulnerability results in machine-readable format. That's exactly what's happening here, and we're simply taking the JSON dataset and passing it through a small formatting script called Snyk2HTML, which is available on GitHub. So this code can be modified to create custom build artifacts or export vulnerability data to CSV, PDF, or other formats, or import directly into a third-party system. And that output also opens the door for lots of other customizations to your security gate. Because CI toolchains tend to use the exit status of each pipeline step to determine whether to fail the build, it's very easy to write scripts to parse Snyk's JSON output and set the exit status according to your own criteria, which can be determined on a per-project basis. For example, custom failure states can be set based on the underlying CVSS score or the presence of vulnerabilities associated with particular CWEs, common weaknesses which might imply more risk in particular applications like public-facing web apps. We've even made this easier by developing some open source tools to parse Snyk's output in a variety of ways that can be dropped straight into your DevOps pipeline. One of these, called Snyk Filter, uses a common utility called JQ to apply custom filters to Snyk vulnerability lists. By adding a custom JQ filter set, you can easily apply exactly the security policy needed and fail your build accordingly. Another example is a tool called Snyk Delta, which works by comparing your test results to a known baseline and then generating the vulnerability diff, or delta, between them. This can be especially useful to compare your build to the previous one, to detect any net new vulnerabilities you've just introduced and fail based on that diff. That's ultimately what I've decided to do in this situation, so I can ensure I'm only blocking my build if there's a uniquely new vulnerability. In order to do that, I just have to specify the Snyk project ID of another project, such as a hardened or a known secure image that's already been approved by my security team. Generating those baselines is easy as well, because any project being monitored by Snyk can be used for comparative purposes. To monitor the container scanned during a build, simply click the Monitor checkbox in the CI plugin, or run Snyk Monitor from the command line and take note of the unique ID of the project that's created. I can pass arguments such as a project name to uniquely identify this build in the UI for future reference. Snyk will continuously test this container snapshot for vulnerabilities on a daily basis and notify you as new issues are detected, just like any other project. As you've probably realized by now, some of these advanced features are more straightforward to use if you simply integrate the Snyk CLI directly in your build pipeline as a shell script. That way you can utilize any combination of additional tools and logic around it to set the appropriate build status. I hope you've enjoyed today's talk about securing your container build and deploy pipeline with Snyk. In my final session, I'll be touching on the last phase of the container SDLC and show how you can use Snyk to monitor vulnerabilities in your container images once they're deployed to production, so stay tuned for that. And if you haven't seen my first talk on integrating Snyk Container in the local developer desktop, I encourage you to take a look at that session as well. Thank you, and as always, stay secure.